Hello, welcome to our lesson 7. In this lesson, we are going to look at relationship between the focal length f and the radius of curvature r of a curved mirror. Shall also look at the mirror formula, sine conversion, and lastly, linear magnification. Let's begin by looking at the relationship between the focal length f and the radius of curvature r of a curved mirror. So let's begin by looking at that using a concave mirror. So we have here our concave mirror. So we shall draw a ray AX to meet a parallel ray AX, a ray parallel to the principal axis. That ray AX parallel to the principal axis, it is going to meet the mirror surface and then it will be reflected according to the law of reflection, and it is going to pass through the focal point or the principal focus. So this C, this ray through C, or this line through C, is going to be meeting this surface normally, because every line that meets the surface of the mirror here, of this curved mirror, will always meet it as 90 degrees or normally. So it means that this is going to be a normal. And so this angle alpha is going to be angle of incidence, and then this angle also is going to be the angle of reflection. So if this is alpha, then this is also going to be alpha by the law of reflection, the second law of reflection. Then also we need to note that CP is equal to R, and then FP is the length, focal length is the focal length, F. Now, I've already said that the angle AXC is equal to the angle CXF by the second law of reflection. And also the angle AXC is equal to the angle XCP. That is because they are alternating angles. Then also, since this angle is equal to that, and we are saying that this angle is equal to this, that means that this is also alpha. So we have alpha here and alpha here. Then alpha plus alpha is equal to alpha, because two interior angles add up to one exterior, one opposite exterior angle. So this is 2 alpha. Now, we also see that if this angle is alpha and this is alpha, it means that this side is equal to that side. So it implies that this is an isosceles triangle. And so CF is equal to FX. So that is equal. And also, we are going to assume that this line is very close. That line AX is very close to the line CP. And so it means that it will be around down here. And so this X will be approximately here. And so the distance FP will be approximately equal to the distance FX. And if those two distances are equal, it implies that if this is equal to that and this is equal to that, it implies that FC is equal to PF, or CF is equal to PF, or FP. So those are going to be equal. Now, if these are equal, CF and FP are equal, it implies that twice of FP gives you CP, but CP is equal to R. So we shall have twice of FP is equal to CP, which is equal to R, and twice of FP is equal to twice of F, because this distance FP is F, and so 2F is equal to R, and therefore R is equal to 2F. So that's the relationship. You can also show that relationship using the convex mirror. Let's see, for the convex mirror, we have the same scenario. Also, we draw a ray parallel to the principal axis, and then that ray is going to be reflected according to the second law of reflection, and then it is going to appear to come from the focal point here. If you remember the rules, all the parallel rays parallel to the principal axis always reflected through the principal focus. And so this is still going to be a normal, because as you see that this line is passing through the center, so it is going to be a normal. It is going to meet this surface normally, and that's why even this ray here is going to be reflected along the same path. So if this is the angle of incidence alpha, this is going to be angle of reflection, alpha. And also, if this is alpha and this is alpha, we know that alpha plus alpha gives you 2 alpha. That's why this is 2 alpha, because they are corresponding. They are corresponding. And also, if this is alpha, even this is alpha. And this is alpha because they are also corresponding. Then you still need to note that if this is alpha, even this is alpha. That is, if the angle BXD is alpha, then the angle CXF is also alpha because they are alternating. So even this is alpha. And also still, we know that FP is the focal length F. And we are also saying that let's make this to be very close to this. And if it is very close, it means that if AX is very close to this line, AX, the ray AX is very close to this line, then also it means that this X is going to be very close here. And if it is very close here, if this X is very close to P, it means that the distance FP is approximately equal to the distance FX. So the same thing is going to happen just like in the previous case, the same scenario. And so if those are equal, it implies that also if this is equal to that and this is equal to this, then FC is approximately equal to FP. And if they are equal, we know that for us to get FP, so FP can, twice of FP will give us the distance from here up to here. Because if this distance from FP is equal to FC, then twice of FP gives us CP, which is equal to R. And therefore, R is equal to 2F, because FP is equal to this small f. So the relationship is also derived in that way. Let's look at the mirror formula. We shall derive the mirror formula using a point object. And we start with a concave mirror. So we have a ray from a point object. A ray from a point object is going to meet this mirror surface at X and is going to be reflected according to the law of reflection. Given that this is going to be the normal, then this is going to be angle of reflection. And so if this is theta, the angle of incidence, this is also going to be theta, the angle of reflection. They are equal. Now let's call this angle alpha, this one beta, and this one gamma. Those are the angles subtended by the object, by this C, and then by the image, where the image is going to be. By the image is going to be gamma. Then also, we are seeing that the object distance is given by U, the image distance is given by V, and then the distance from C to P is F. That one we know. Sorry, is C to P is R, and it is twice of F. Now, we are going to assume that this X is close to P, and if it is close to P, then the distance XP is approximately equal to that height H. And so, we shall be in position to use that H instead of XP. Now, using this triangle OXC, we can see that alpha plus theta is equal to beta. And therefore theta is equal to beta minus alpha. That's our first equation. Then also using the triangle OXI, using the triangle CXI, we shall also see that theta plus beta is equal to gamma, and therefore theta can also be given as gamma minus beta. That's our second equation. Now if we equate the two equations, we shall have beta minus alpha being equal to gamma minus beta. And if we take beta, make beta the subject, that is, if we make beta the subject, we shall have twice of beta is going to be equal to gamma plus alpha. Now we are going to replace for these ones, for beta, gamma, and the alpha. We know that alpha is going to be opposite, but before we say that, we need to note that these alpha, beta, and gamma are small angles measured in radians. And if they are small angles measured in radians, then the tan of alpha is approximately equal to alpha, and tan of beta is approximately equal to beta, and tan of gamma is approximately equal to gamma. And so if I want to get this, alpha is going to be approximately equal to tan of alpha, which is opposite h over adjacent, which is OP, which is actually U. And also beta is equal to tan of beta, which is opposite, which is h over adjacent, which is CP, which is approximately CP, which is actually R. And also tan of gamma is opposite, which is h over adjacent, which is IP, which IP is actually the V. And if we replace that here, then we shall have this. So we are replacing that. So wherever there is beta, I'm putting h over CP, which is actually R. And so the h will cancel because then on both sides, so you can divide through by h and then move, and then we replace for CP with R, and then this is V, IP is V, so that is this one here. So we shall have 1 over IP, which is actually 1 over V, and then h has gone, so we have 1 over OP, which is actually 1 over U, according to this. And therefore, we shall also replace for R is equal to 2F, where R is, we put 2F, and shall have 2 over 2F is equal to 1 over U plus 1 over V. Hence, 1 over F is equal to 1 over U plus 1 over V. And this is the mirror formula. We shall also do the same for a convex mirror. So for the convex mirror, we shall also have this same procedure. We shall have this alpha will be angle subtended by the object, gamma angle subtended by the image, and beta angle subtended by the C normal through C. So a ray from this point object O is going to be reflected, and then to appear to come from here, and that's where the image is going to be, and then this is going to be the normal. So if this is theta, even this is theta, the same procedure. And also if x is very close to P, then this distance h is approximately the distance xp. And also the same thing, we are going to consider the triangle OXI. If you consider the triangle OXI and also the triangle OXC, we shall come up with two equations. So let's start by looking at the triangle OXC. So we shall see that will give us alpha plus beta is going to be equal to theta, and therefore theta is going to be equal to alpha plus beta. And also we shall see that twice of theta, if you consider this other triangle, we shall see twice of theta is going to be alpha plus gamma, equal to alpha plus gamma, because two interior angles adds up to one opposite exterior angle. So you shall have those two. So if you look at those two equations, you can simplify these two equations to come up with one equation. So we can multiply equation 1 by 2 and then combine with the second equation. So let me try to show that, how we can come up with that. So we shall get that. Let me get a pen here. So we shall have twice of theta is going to be equal to twice of beta plus twice of alpha. Now remember, we have down here, we have 2 theta also. That is from equation 2, we have 2 theta being equal to gamma plus alpha. So you can see this is equal to that. So we shall equate this equation to that equation. If you equate this equation to this, it means that we are going to have 2 beta. We're going to have 2 beta plus 2 alpha. But now I want to take the alpha the other side, so I can just equate is equal to gamma plus alpha, and then minus, because the 2 alpha will go to the opposite side, and shall have it will become a minus 2 alpha, minus 2 alpha, and therefore if we subtract that, we shall have 2 beta being equal to gamma minus alpha. So the 2 equations will reduce to that. So equation 1 and equation 2 will reduce to that. So we shall get that finally. 2 beta minus, so 2 beta is equal to gamma minus alpha. So after getting that, we shall also still replace. If I want to get alpha, alpha is going to be opposite, which is h, over OP, which is actually u, and also gamma is equal to opposite, which is h, over adjacent, which is v, and then beta is equal to opposite, which is h, over adjacent, which is r. But we need to note that since these are imaginary lines, this side we shall have negative, so this v will be negative because this image is virtual, and also the center of curvature is also virtual, so this radius of curvature is also virtual. So this is going to be negative, and this is also going to be negative. So we are going to be replacing negative for v and r, and then we shall have the same conditions there. And when we simplify, you can see that where there is r we are putting negative, where there is v also putting negative, and then we shall multiply through by negative and they become positive. Then we replace for 2f, and we shall have 2f. 2 over 2f is equal to 1 over u plus 1 over v, and therefore 1 over f is equal to 1 over u plus 1 over v. Yes, look this. So we have seen that in that case, u is the object distance, v is the image distance, and f is the focal length. Let's continue and look at the sign convention. So we need to know the first sign convention we are talking about here is that distances of real objects and real images are positive. That means that u and v are positive for real image and real object. And also the distances for virtual objects and virtual images are negative. That is to say, u and v for virtual objects and virtual images are negative. And also the focal length of a concave mirror is positive, and the focal length of a convex mirror is negative. So those sign conventions are very, very important in the calculations. You need to take note of them. Let's look at linear magnification lastly. So linear magnification, we are going to define linear magnification as the ratio of the image height to the object height, or you can also define it as the ratio of the image size to the object size. And therefore we shall get our magnification m, represented by m, as height of image over height of object. We shall also be able to show that magnification can also be given as the image distance over the object distance. Shall also be able to show that m is equal to image distance over object distance, v over u. This can be shown, and we are going to show it. We're going to prove that. So we shall consider that ray AP, which is incident on this pole. We shall draw this ray, and it's going to be reflected at the same angle with which it makes with the principal axis. And so this is, if this is theta, even this is going to be theta. And then another ray through still this object, and C is going to be reflected along the same path, hence forming this image of height h1. And therefore we shall have this image of height h1, and then the object is of height h0. So if you consider the triangle OAP, we shall get tan theta is going to be opposite, which is h naught, over adjacent, which is OP, which is the same as u. And if we want to get this one, this triangle, if you use this triangle IBP, we shall also get tan theta as opposite, which is h1 over adjacent, which is actually v. So we shall come up with two equations. And simplifying these two equations, if we equate the two equations, we shall see that our h naught over u is equal to h1 over v. And if we cross multiply, we shall have v over u is equal to h1 over h naught. But remember, h1 over h naught is equal to m, the magnification. Therefore, the magnification will be equal to v over u, which is the same as h1 over h naught. Thank you for your attention. See you in the next lesson.